Ma'am, can we start? Subhashini, ma'am?
Yeah.
Yes, ma'am. So, good evening to everyone. I welcome you all to the fourth day of this ATAL online FDP on smart systems and emerging technologies in Industry 4.0. Today, first, we have the session on advanced hardware technologies and security in embedded systems by Mrs. N. Subhashini, engineering specialist, Curtis Wright Corporation, Ottawa, Canada, followed by the session on Engineering for the Real World, Ethical, Domain Aware AI and IoT Solutions for Industry 4.0 by Mr. D. Sivapunniyam, founder and CEO, Signatech, Milwaukee, USA. Now I invite Mrs. S. Hemalata, Assistant Professor of EC Department, to frame out the profile of Mrs. N. Subhashini. Ma'am, please.
Good evening, everyone. It gives me a great pleasure to introduce the resource person for this section. Mrs. N. Subhashini is currently working as an engineering specialist at Curtis Wright Corporation, a globally renowned organization specializing in engineering solutions for aerospace, defense, and industrial markets. Based in Ottawa, Canada, she brings with her a solid background in electronics, debugging technologies, and automation solutions. With over a decade of experience across multiple roles in both public and private sectors, Mr. Subhashni had held key technical positions including Debug Tech at Sanmina from the year 2022 to 2024, Automation Delivery Associate at UX Explore Incorporation in the year of 2022, freelance engineering roles prior to her industry placements. Her education qualification reflects a diverse and interdisciplinary foundation. She had did his Master of Engineering in Power Electronics from Jerusalem College of Engineering from the year 2012 to 2014. An MSc in Information Technology from Anna University from the year 2009 to 2011. B in Electrical and Electronics Engineering from Madurai Kamarajar University from the year 1997 to 2001. With her extensive technical background and hands-on experience in electronic systems, power electronics, and engineering automation, she brings a practical and insightful perspective to the field. Her contribution make her a valuable resource person for technical talk, industrial interaction sections, and knowledge shared platform focused on electronics, embedded systems, industrial automation, and power system. On behalf of all of us, I am warmly welcome Mrs. N. Subhashni as a resource person for this section and invite her to handle the section. Please, ma'am.
Thank you, Hemalata. Thank you for your intro, but it's huge intro. I don't know whether I deserve it or not. I just share my information that I know very little. And I thank Jasmine as well. Thank you.
Thank you, ma'am.
Yeah,
Thank you, ma'am.
I'll share my screen. Okay. One second, please. So hope you all see my screen.
Yes, ma'am, it's visible.
Yeah.
Yes, ma'am.
So first of all, good evening all. I'm very happy to be here presenting some little information that I know. And at this point, I want to share something that back in 2009, I was a part of New Prince Shri Bhavani College of Engineering. I worked in your institution for a few months. So I'm back to be here after decades. Thank you. So coming to this session, we are going to discuss about the advanced hardware technologies and security in embedded system. So when talking about the growth of hardware innovations, we cannot they are both linked with software advancements. Hardware without powerful software is merely empty shell. So when talking about embedded system, ma'am, can you stop my video that
Yes, ma'am.
yeah, thank you so much.
Okay.
So when talking about embedded system, they both are like the railway tracks, like one without the other is not at all possible. So when we are talking about hardware components in embedded system, especially software components, it is not possible. The innovation and technology is not possible without hardware components that we all know. So what is the layered structure of an embedded system? So when we talk about the embedded system, we build some system with all the embedded components in a PCB or in a motherboard. So after developing or producing the PCB boards or the embedded boards, we need some operating system to have the produced model to work. And then upon the operating system, we apply some application software related to the product, that what it is meant to work for. So it is like suppose just imagine that we build an automated car. So after building an automated car, it is like the base. It is like the base of the system. After producing the automatic car, we need some basic functions to be started initially. That is the operating system. That is the key. When we put the key on the car starts. So once the car starts and keep ready for us to move. So like the key of the system, the operating system helps the embedded. That is, it checks whether the petrol is full, whether all the doors are locked, and other basic functions of the cars are ready to move. So that is the work of an operating system. Then upon that, like a driver, not a driver, it is an automated car, like some control software is needed to tell the car, that is to instruct the car to go which way, go straight, go left, or go right. So every application software is like an driver or instruction. It gives instructions to the operating system what to do. So next comes, what are all the operating systems? So this is a very good field that you can explore at. There are so many operating systems that are meant for embedded systems, like multitasking, OS, Linux, that is embedded Linux, real-time operating systems like VXBox, single operating system, and we all know that we have Android mobiles that has an own software. It is an embedded software that is meant for Android phones. And then comes rate monotonic operating system. So there are so many operating systems that are meant for embedded. So particularly Linux, embedded C, and VxWorks. There are so many operating systems. They are helping in today's technologies to explore further. So we all know how the technology evolves. So an advanced hardware technologies encompass, that is, it possesses the cutting edge developments. That is a technology, that the technologies that we are using in today's world is the latest features and capabilities that the technology has. So it is best in class. As of today, it is best in class, industry leading technology that innovates and pushes the boundaries of current knowledge in computer hardware, semiconductor design, and related fields, that push the boundaries of performance, efficiency, and functionality. Yeah. So it pushes back the older technology, and there comes a new technology in today's world, which is best as of today. So what is the technology? Then if we attain some technology, what next? Is what technology is growing so fast. So we are pushing the boundaries, and we are going forward in exploring the technology. This is how the technology evolves. So we all know semiconductor. Yeah, the semiconductor, we know it power everything. What are all we are using in today's world? And today's world, it is all related to semiconductors. That is from smartphones that we are using, supercomputers, space stations, aircrafts. In every automation fields that we need semiconductors. So with technological innovations, advancement in next generation processors. Yeah, for every embedded systems, we need a different kind of processor to explore and to reach what next in the technological field. So in next generation processors and the transformative impact of artificial intelligence on chip design. This is a very crucial and very important part in today's AI technology, that is chip design. We'll talk about this later. And the field that continues to evolve at a very fast pace. Then, yeah, usually when we talk about today's world, we always talk about technology that is related to software. No, that is not true. So semiconductors, they are the unsung heroes of the technological world, because without semiconductors or without embedded systems, no new technology cannot evolve. So when we are talking about today's technology, it is not about software alone, it is about embedded as well. So they work behind the scenes to power everything that we all know, from toys and smartphones to cars and thermostats, right? So in recent years, they have enabled breakthrough technologies, because today's world is an AI world, and there are so many machine learning languages that are being developed that needs to aid AI. Taking the digital revolution to the next level will require even more advanced chips with greater computational power and memory capacity that so many technological giants are working on. So first, actually, I want to tell you that I have chosen the very general topic like advanced embedded technologies. There are so many advanced embedded technologies involved, but today I'm going to discuss with you all about the chip designs that are the latest chips, that what they're using for the production of an embedded system. So I start with chip design. What are all the chips that are all aiding AI in today's world? So FPGA, hope you have all known about this FPGA concept, that is field programmable gate array. It is related to programmable logic family that you have all studied about. So field programmable gate, usually the difference between other PLDs, programmable logic devices, and this FPGA is that it is field programmable. All other PLDs, they cannot be erased once they develop, and if some new technologies comes, they have to dump the older PLDs. So FPGA, it is one of the defining features of FPGA is its ability to be programmed and reprogrammed on site due to programmable RAM integrated within each chip. That is the name field programmable gate array. The field programmable signifies the ability to program the device post manufacturing. That is, after manufacturing the chip and at the site and at the customer side, they can implement their own software. And if innovation, if they need any upgrades on the system regarding FPGA, they can do it by themselves, uh, erasing the older software that is implemented, and they can program the newer version of the software into the FPGA. Initially, during setup, the FPGA loads configuration data from an external non-volatile memory. That is, we have all known about erasable, programmable, read-only memory. So each and every FPGA has its erasable, programmable, read-only memory. So if some chip needs to work, it gets instructions from where? It gets its instruction from all this read-only memories. So this FPGA has its own read-only memories that can be erased and programmed every time. Once the board switch is powered off, the all configuration setup in the read-only memory got erased. So once it is powered on, again this FPGA gets its instructions from the PROM and executes its functions. So field program, as I tell you, field programmable means it programs each time at the customer site after manufacturing. What is gate array? Gate array indicates that the FPGA comprises a vast number of basic logic blocks. We all know that programmable logic devices holds so many logic devices, and it holds flip-flops to store the results of those logic devices. See, these logic blocks can be interconnected in unique configurations, enabling tailored functionality. So FPGA offers significant flexibility for a wide range of applications in digital design. This characteristic allows the FPGA to be reused, accommodating changes in design or function without needing newer hardware. Like other PLDs, they need newer hardware if they go to changes in design. So unlike traditional methods that require specific programming devices, FPGAs can be programmed using standard EEPROM or PROM programmers, making them more accessible for modifications and updates. So these FPGAs, they have transformed the landscape of digital electronics, providing engineers with the ability to create adaptable and efficient circuits. Their history reflects a continuous evolution driven by technological advancements and the growing demand for customizable solutions in various industries. As FPGAs, they continue to develop, they remain integral. That is, they always mingle with the modern computing and digital designs. It always cooperates with the future technologies because, yeah, it is reprogrammable. So it is so flexible. These FPGAs are so flexible for this innovations for researchers. Like we say, they are all useful in building a prototype. Suppose some researchers are going on, every time they implement some program and they test the output. So they cannot demolish after each test. They cannot demolish the circuit, demolish the system. So for that purpose, FPGAs are playing a crucial role, that every time they can be reprogrammed So it helps very much in research field. So we all know, you may think that whether FPGAs recently developed a chip. No, this concept has been evolved around 1980s itself. They're revolutionizing digital electronics with their flexibility and programmability. So Altera, was founded in 1983. This is the company that introduced FPGA to the world in 1984. The first FPGA they've developed was EP300. How did they erase the program they have implemented on this FPGA is the mean by splashing or focusing some ultraviolet rays on the chip, and they erase the EEPROM cells and they reprogram it again. This is how this FPGA concept they started in 1984. So then Xilinx, this is the very much leader in this field, in this FPGA production manufacturing. Xilinx is leading the world even today. So it produced the first commercially viable field programmable gate array in 1985. It was named as XC2064. It had programmable gates and programmable interconnects between gates and the beginnings of a new technology and market. So when they produced and they marketed, the first FPGA had only 64 configurable logic blocks with 3 input lookup tables. What is a lookup table? As we all know, it is a truth table, what we call. So since 2019, this modern generation of FPGAs have been integrated with other architectures like AI engines to target workloads in artificial intelligence domain that we will discuss later on. So yeah, so I have told you what are all the basic architecture of FPGA. So what are all the blocks that are being squeezed inside this chip? What are all the components they are inside the FPGA? So we are going to just discuss about this. So inside every FPGA, it has configurable logical block that is shown here. That is the blue blocks that are highlighted. They are all the configurable logic blocks, and they have the green color small boxes or switches, and the outer part is the input output ports. This is the basic concept of FPGA. These are all the basic building blocks inside the FPGA. That is configurable logic blocks. The brain and heart of the FPGA is configurable logic blocks, and then switches and input output connects. So what is configurable logic blocks? Configurable logic blocks holds the logical gates like AND gate or gates, and it has flip-flops as well as a memory unit. So configurable logic block, it contains logic inputs and outputs. It implements the user-defined logic. Yeah. So inside each CLB, they have the logical circuits. So they connect the circuits according to the need of the circuit. Whatever the designer is implementing, the software, it is implemented is inside each CLB blocks. They implement the structural design of the logical gates inside each CLB blocks. So each CLB blocks, they produce an output when some input comes in. So that outputs are being stored in the flip-flop, which is a register. It is all being stored. And after everything has its own output, this switch, these are all the interconnects. These allows to connect, the outputs are being connected with each other, and these switches allows and blocks according to its need. So yeah, So in this modern FPGA, so initially they have developed FPGA, but that they don't have their own memories embedded inside each FPGA chip. Instead, it got its memory from the external memory chips. So nowadays, I am talking about, this is a standalone FPGA. So in the standalone FPGA, each FPGA nowadays have its own memories inside. So why these memories? They help to enhance the device's computational efficiency. It makes a device fast and it handles so many millions of data by itself. So it has its own, also it has its phase lock loop generators. So no signal is being lost, no signal is being missed. So each has its own dual port RAMs and it has its own accumulatable blocks and high speed serial trans receivers. That is, it has its high speed input output interconnects. So this is what there are two kinds of FPGA that we can talk about. One is standalone FPGA and the other one is eFPGA. So as I told you, the standalone FPGA, it has its own memory, it has its own input output devices, it has its own interconnects within itself. So it is decided for particular job that it is meant to do. So this is different, and there is one more FPGA. We can call it as eFPGA. What is eFPGA? What is the difference between that standalone FPGA and the eFPGA? So we'll talk about a concept called a system on chip later, but these eFPGAs are included in certain chips along with the other chips. Instead of standalone, it is being embedded in a other chip along with other chips. So it doesn't have any memories or any input output ports of itself. Instead, it shares its memories and the bus connects with other chips that are being included in the particular chip, that can be integrated into an ASIC or SOC to provide programmable logic capabilities. As I told you before, as like traditional FPGA chips, components like GPIOs, that is general purpose input output ports, or serializing and deserializing ports and physical connects, or generally are not integrated on the SOC or ASICs with this eFPGA. So with eFPGA, you have the flexibility of defining the quantity of LUTs, embedded memories, register, and DSP blocks according to your needs. So before going into that, one of the primary uses of FPGA is in the development of pilot samples for ASCII circuits, that is application-specific IC circuits, whether fully customized or semi-customized. This step is crucial for testing and refining the circuit design before committing to mass production, thus reducing potential risks and overheat costs. So this overheat is the a particular disadvantage that is developers has to combat with. So FPGAs are densely packed with numerous flip-flops and input-output pins, which provide the necessary resources for a wide range of digital applications. This abundance of hardware resources allows for greater design flexibility and scalability, as I told you before. Among the options for creating ASIC circuits, FPGA stands out due to its short design cycle. It's not only reduces development costs, but also lowers the risk typically associated with the design and implementation of custom circuitry. The use of high-speed CMOS technology in FPGAs results in low power consumption, making them an energy-efficient choice. Additionally, their compatibility with both CMOS and TTL levels ensures that they can integrate smoothly with other existing technologies. That is, the developing technologies of the world. They always they go ahead, go smoothly with those existing technologies. This capability to update and adapt the hardware remotely adds a layer of flexibility and future proofing, ensuring that the FPGA can evolve alongside technological advances and changing requirements of the circuit. So we have talked about FPGA. This is one kind of chip that is assisting today's AI technology. So we have done with one chip, that is FPGA. Then we are going to go for another topic, that is MPSOC. What is MPSOC? As the name suggests, it is multiprocessor system on chip. A system on chip. What is a system on chip? So FPGA, when we talked about standalone FPGA, it is a separate chip. So we talked about eFPGA, that I told you that this eFPGA will go along with other devices inside a single chip. So this is the concept. So this is a chip. So inside the chip, we have so many processors, so many input output devices, so many memories. Along with them, we also include FPGA. So putting everything together inside a single chip is called as multiprocessor system on chip. Is an integrated circuit that unites all parts of a computer or electronic device onto a single chip. The SoC usually has a central processing unit, not a central processing unit alone. Nowadays, we include GPUs and APUs, real-time processors as well. The best feature of this SoCs is their consolidation of multiple hardware components onto a single chip, which allows for reducing system complexity and size of the system and power consumption versus traditional multi-chip solutions. So, why it is essential for this modern high-performance applications? So the performance needs. Increasing demands for performance in applications require the use of multiprocessor systems. Traditional single processors are insufficient for any modern tasks. So they cannot handle so much of data and the fast processing systems that needs for today's AI technology. So in the world of integrated circuits, the term system on chip and multiprocessor system on chip are common. We will explore the fundamentals of SoC and MPSOC, explore their key features and highlight the differences between them. So as I told you, these multiprocessors, because we are including many processors inside a single chip, what it is meant for? It automatically, it helps for superior performance, it outperforming the fastest uniprocessor configurations, thereby achieving better processing capabilities. So I show you, this is the picture shows you the FPGA, the MPSOC. This is Xilinx. I told you this company is the leading master in the manufacture of FPGAs. So this inside this single chip, it has so many processors inside, so many memories inside, and DSPs inside, and input output ports inside. So this is a single chip that manages the so many functions of a circuit. So then what are all these small components that is being embedded in the board? So these the components that are kept around this MPSOC are all power controllers and some memory ROMs, because initially, as I told you, we need some processors to make the system get ready for the function. So once it is powered on, these devices, they powered on and they check if they have any power shorts in the board, or if they have any functional problem in the board, everything. So these other, the chips around it are all the either DC to DC step down controller transformers or step up converters. So the MP-SOC is designed to integrate multiprocessing units into a single chip, as I told before. So taking a regular computer, for instance, on its PCB, you would have separate components such as CPU. We all know that. We have our desktops. What it has its separate CPU, separate GPUs, RAM, and plethora of other circuitry mounted in sockets or slots within the motherboard. These are integrated to work seamlessly with each other using circuits called buses. So the CPU is a microprocessor that performs all the mathematical computations or the processing in a computer, as we all know. Now take all the required electronic circuitry of those components and combine them together and put it inside a single chip instead of a big PCB. See, the bigger PCB in today's world has been squeezed into a smaller chip. So whatever the big CPUs that we have for our computers have been reduced to a smaller chip. See how the technology is developing. So now take all the required electronic circuitry of those components and combine it all into this small single chip. This is simply an SoC or multiple SoC. That is system on chip. So when we are talking about multiprocessor system on chip, so what are all the processors that go with this, that can go inside this MP-SOC? What are all the processors that we can embed inside this single chip? As we all know, we know central processing unit is the processor that we all know, that it is the main brain of the computer. But the only thing is that this central processing unit always process the data in a serial manner, that is one by one. So when we are talking about today's world, mostly they are not using the CPUs unless they need it, because they cannot handle this very much speed processing, and they cannot handle the bigger data in today's world. But in some cases, they are using the central processing units because this handles everything in a serial manner. Then, so that they are going for graphical processing units. You all know, for all the advances made with CPUs, they still have shortcomings, as I told you. However, GPUs, they multiple data to be processed simultaneously. That is, they handle data parallelly. If instructions comes in, so all the processors that are embedded inside the chip gets the same instruction at the same time, and they follow and they work with the instruction along one with each other. So it will not wait like CPUs did. If one chip completes its work, then comes other chip. No, all the chips work at the same time. That is the concept of GPUs. That is, it works parallelly. CPUs work in a serial manner. So then comes accelerated processing unit. So some people, they need CPU also. So what they are doing is that they are combining, they are producing a new kind of processing unit called accelerated processing unit that combines both CPU and graphical processing unit inside a single chip. Not only does this reduce cost, but it improves its efficiency also, minimizing the physical distance between the two. Anyway, if we have CPUs and GPUs in our systems that stand alone, the desktops, if we want to connect those two processors, we need some buses to be connected, which have some delays getting the information between the two. So this minimizing the physical distance between the two, because they are coming inside the single chip, they're coming together. So this enables faster data transfer and increase their performance. As the technology is becoming more and more advanced, the tightly coupled circuits have many pros on extended hardware itself. So I have talked about central processing unit, graphical GPUs, and accelerated processing unit. That is, they are combining both CPU and GPU together and making a new processor. And as you all know, digital signal processor. Yeah, some cases we need digital signal processor also. You all know it is a specialized microprocessor chip with its architecture optimized for the operational needs of digital signal processing. They are widely used in audio signal processing, telecommunication, digital image processing, radars, sonar, and speech recognition systems, and all other systems like mobiles, television, etc. So you have all known about this DSPs. I don't want to explore it anymore. And another processing system is called neural processing system, which is a very much new processor that is being used in today's AI world. It is a special processor used for handling this AI and machine learning workloads like speech recognition and object detection. MPUs can process large amount of data in parallel. That is very much important. That is not possible in CPUs and similar to a GPU, but they are better than GPUs. Because this AI and ML processing tasks, they need more practices. They need more workloads. They need to work on parallel. They need to develop a protocol. What comes if this movement comes, then this should be the reaction. So we have to feed so many data to it, so that how much data we feed into the processor, it has more speed, it is more efficient. Then this is the recent trend in the processor is real-time processing unit. This is very much important, right? In today's space technologies or aerospace, wherever in researchers, that real-time, it has to act to the real inputs that it is getting. It should immediately react to the input it is getting on spot. So these RPUs used in versatile devices provides improved performances at all improved safety levels. However, for real-time applications which require a high level of safety, reliability, and determinism, real-time processing unit is used with a lockstep processor subsystem. So they are very much used in military applications nowadays and research fields. So this is the latest MPSOC device that is being released by AMD, a leading leader in the field of MPSOC. So they have proposed this system today that it has inside the single chip. As I show you, it has this PLD, programmable logic. This is an eFPGA that is embedded inside the chip. And we have RPUs. And we have RP, the processing system is an RPU, real-time processing unit. This is the real-time processing unit. This is an accelerated processing unit. As I told you before, it combines both CPUs and GPUs. Also, it needs some other GPU to handle other sessions as well. So they are having separate GPU also for some common needs. So they have eMMC memory, and they have this input output memory blocks. This is a memory block, so it holds so much amount of data inside it. So they have DP ports for the connection between the FPGA devices and the processors through a central switch. This is a power management unit and everything. Also in today's circuits, they have a chip called a technology called intelligent platform management technology. What it is, the meaning of that is it controls the processor without, even if it is powered off, we can control the processor from anywhere else. So as I told you, this is the latest MP-SOC that is in today's world, that is not being widely used, but they have proposed this design, and AMD is practicing it. So you may ask whether we need to go for all the processors in today's world. No, that is not the case. We can choose what according to our need, or according to the functions of the board that it is meant for. We can choose whatever processors we need for the system. So there are so many advantages and disadvantages there between these among these processors, and we can choose the processor, the combination of processor as we need. As I told you, there are common uses. CPU, it is a common, it is used for common maintenance of the system, that is power maintenance, or getting the system ready for the work. GPUs, as you all know, it is used in gaming, video rendering, AI computing, and in accelerated processing unit also. Sorry, it is used for entry-level gaming and multimedia. The newer version is that NPU, it is used for AI tasks, voice recognition, and robotics. And apart from this, now we have RPUs, real time processing unit. So these are all the types of processors that we can go use for the MP-SOC chip. So the conceptions are all the parallel processing programming, a single program. As I told you, in this MP-SOC, a single program that a developer writes for this MP-SOC chip, it handles all the multiple processor. Instead of writing separate programs for separate chips, we can handle all the processes that we put inside this chip using a single program. It is, for example, I tell you, it is a cluster, like how we connect a set of computers over a local area network that function as a single large multiprocessor. Also, the very big concept is that it has shared memory. So each processor or each FPGA that we put inside this MP-SOC will not need a separate memory, separate input output. No, they all the processors that we put inside this MP-SOC, that FPGA, that eFPGA that we have embedded inside this MP-SOC, they share memory. A memory for a parallel processor with a single address space, implying implicit communications with loads and stores. As I told you, in MP-SOC market, the leading are Xilinx, Intel, NVIDIA. I have forgot to add AMD. It is also a leading master in this field. So far we have completed two. One is SOC, that is one is FPGA, one is MP-SOC. Now the next chip architecture is system in package. I have told you before, what is the difference between the thing that we have talked before, MP-SOC, multiprocessor system on chip. So inside a single chip, we bring all the processors, FPGAs, they have embedded inside a single chip. But in system in package, it is different. We have different, it is a type of advanced semiconductor packaging technology in which multiple integrated ICs and electronic components, such as what are all we put inside SOC, that is processors, memories, FPGA, whatever it may be, we can put everything together as a package. We get processors separately, we get FPGA separately, we get RF modules separately, everything we get a package from different vendors and put them all together as a single package. So this is driving AI, 5G, and Internet of Things and high performance computing demands in today's world. So this is the difference between what is MPSOC and what is SIP. MPSOC is system on chip. That is inside chip, we are bringing all components together. System in package, we are putting all systems, we are packaging, we are connecting externally everything and putting it as a package and delivering the part. So this is the difference between these two. And also in SIP, it includes everything because this is a package. We can bring everything together. It will not bother about the size of the chip. It is a package. It can be of any size. So it can include CPU, memory, sensor, or a analog, whatever it is. But here in MPSOC, it only includes processors, accelerators, that is FPGAs, memories. That's it. So this is the difference between that two, that system on chip and SIP. That system on chip, it has in this single chip, everything comes in. Everything comes in. But in SIP, you have every separate. This is a processor. This is meant for separate function. This may be CPU. This may be GPU. They are all put separately and packing together. These are all two different technologies. So now, the other master in today's world is chiplets. So far, we have discussed about chips, that is FPGA, MPSOC, they are all chip. Then what is chiplets? Now today's world is moving on to, instead of chips, they are using chiplets. Traditionally, SOCs have been implemented as a single large monolithic die, as I have told before, but these chiplets are miniatures. A smaller silicon dies known as chiplets, which are connected and integrated into a single package to form a multi-die system. That I'll talk you later. See, this is the main difference. The MPSOC or FPGA, when you see on the left hand side, this is their monolithic die. That is, in a single die, they just embedded, they just share this a single chip. They just manufacture as a single chip. But here, when we come to chiplets, they are all what a chiplet, you have to know that it takes some advantages from SOC and some advantages from SIP. They are putting it together. It is a package, but the package comes in a single chip. Instead of bigger package, we are reducing it to a single chip, and it is called as chiplets. Every CPU, GPU, they have all reduced. It is miniatures, like what we put in MPSOC. These are all the miniatures of those circuits and we have separate dies for it. When we see here, it shares the same die. When we see here, it shares the different dies. Everything is separate. This is separate. This is separate IC. This is separate IC. This is separate IC. This is separate IC. But here, it is a single IC. So what is the difference? What is the advantage of using chiplet? Size. The first thing is size. And today's world, the resources that we are getting, the wafers, it is going on, the cost is so higher. So when consider here, when one part got failed or one part got damaged, the whole chip we have to dump. But when you come to chiplets, when we find any difficulty with the CPU or with this GPU, we can just remove that part and we can insert the other part. Otherwise, when we need any updates in GPUs or in memories, we can go ahead, remove that, and we can add advanced chip that we need. So for any other upgrades or any other damages, these chiplets are getting more attraction in today's world. So as you can see on the right hand side, it is the image of the chiplet, that this is a single chip. This is CPU or whatever it may be. These are all the memories. So everything, they are separate, but they are coming inside a smaller chip. this picture, so you may think it is very big. No, it is a very small chip that we can include everything inside a small chip. This is the chip. Not these are all. These are all the outside memory controlling units and power controlling units. This is a single chip. We have the main processor, memories, everything as a separate chips. So even if this chip got damaged or if chip got screwed up, we can just remove that and replace it with a newer chip. This cannot be done in MPSOC. Yeah, these are all the key advantages. They are all cost efficient in manufacturing and reduced power consumption. It allows designer to mix and match chiplets, fostering innovation and speed in product development. Yeah, these chiplets are also have their own bottlenecks because the connection, the interconnect is a very big threat or very big bottleneck for this manufacturing industries. So they are still researching on those interconnects inside this chiplets. As I told you, this is MPSOC chip or MPSOC. So if you anything get damaged anywhere, the whole chip is useless. But here we can remove it. So if the yield is 0, reject yield is 0, here the reject yield is 75%. So then so far we have discussed about the chips that aids in today's technology. First, we have talked about FPGA. Then we talked about system on chip. Then we talked about system and package. Then chiplets. We have discussed 4 important chip technologies in today's embedded systems. Then finally, we comes to security enhancement in embedded system. So, what are all the security, why it is important? Security in the embedded system is crucial as the system increasingly become targets for cyber attacks, necessitating robust security enhancements. Sorry. So what is embedded security? Embedded system security is a design methodology, implementation, and commitment that companies embrace to limit the threat exposure of the device that they produce. The data the device produce and the data they get, everything has to be protected. So security for embedded devices is a full life cycle responsibility. It is not about the security till manufacturing. No, it is a lifelong responsibility that we have to protect the system. It starts well before the first line of code is written, includes protection in case a device falls into hands of attacker. What happens if the device falls into hands of attacker? What the device has to be done? What and continues until the device has been decommissioned. So, securing the connected world. As the number of connected devices grows, security has become a top priority. The development of secure embedded system is critical, especially with regulations. They have brought so many regulations like EU Cyber Security Act. Security by design approach is essential, integrating protections like secure boot, hardware encryption, and trusted execution environments. These systems prevent tampering and unauthorized access while ensuring sensitive data remains secure through end-to-end encryption. Additionally, there are so many protocols and there are so many multi-factor authentication that helps verifies user identities and restrict access. Also, you have hardware security modules and over the year updates. As I don't know, you remember that I have mentioned about TPM technologies before. That is sorry, IPM technology, intelligent platform management. I've told you, without powering on the device, we can control the device using the IPM technology. It comes under the over the year update, over the year concept. That is, wherever we may be, we can update the software. Like how we update our laptop and Windows have been updated in timely manner. It is also the over-ear update ensuring device. So these comprehensive approaches ensures embedded systems stay resilient and trustworthy in an increasing connected world. When we are talking about security, this is the basic mantra of or basic principle of today's security, embedded security: confidentiality, integrity, availability. So we will talk about this now. Confidentiality is, as you all know, we have to protect the privacy of data in the embedded system. This includes the data in motion, the data they are processing, the data on the network. Everything has to be protected. So we have to make sure that they are all protected. Then integrity. Integrity implementations, that they ensure that the embedded devices cannot be modified or deleted by an attacker. This includes data being generated or consumed by the embedded device as well as its programming data. Yeah, well, then comes availability. The availability implementations ensure that an embedded device performs its intended function. This means it should not get way out of the function that is actually meant to do. It should not get diverted into, or it should not uh, do any suspicious activity. It should not produce any suspicious codes as well. It should not go to any suspicious network as well. This means an attacker cannot change a device's intended functional purposes. This is of paramount importance to devices that perform life or mission critical tasks like military services. So when we are talking about, before we have talked about chiplet architecture, that is, we are putting single chips, that is microchips or miniatures inside a single chip, miniature processor, miniature FPGAs, miniature memories inside a single chip, and we call it as a chiplet architecture. This chiplet architecture is a specific, it has specific security challenges because we are getting each and every chiplet inside the chip. We are getting from different vendors, and we are putting them together to form a chiplet. So when we are getting that chiplets from different vendors, we should be make sure the vendors are trustworthy persons. So we have to make a strong agreement with those vendors on this security concern. So for that, today's security, there are so many security measures there. They have been using it today. In this, we have to, one is risk. I am going to talk about just two because we are getting late. We are running out of time. So there are two: risk B and secure boot. Risk B, it is a kind of architecture. This is meant for processors. It is an open architecture providing customizable designs for embedded systems. Its modularity allows developers to optimize performance while ensuring low power consumption. A favorable choice for various applications, including Internet of Things devices and high performance computing. Basically, this risk-free architecture is meant for today's processors. How to protect, how it has to be acted to the incoming data, how it has to block the insecure data. Then comes secure boot. Yeah, whenever the system has to boot, the system has to start to work, it has to make sure that it gets the correct instruction to work on. So security boot is a critical security feature that ensures the device only runs a trusted software. That is the security boot. The device has to make sure this is a trustworthy software. We can start our work during the booting process. It verifies the integrity of the firmware before it executes, helping to prevent malicious attacks and unauthorized firmware modifications. So when implementing secure boot in embedded system, developers must create a chain of trust starting from the hardware level. This involves cryptographic keys to sign boot images, validating them during the boot sequence, thereby ensuring that the system remains secure from start to finish. So these are all the technologies that we have talked about, what we are using in today's world. Then what would be the next stage? What after chiplet? What will happen after chiplet? What is in research in today's world is that quantum chips. This is the future. This is the future of embedded system. What is a quantum chip? These are all processors. These are all also processors that utilize quantum mechanics for computations instead of classical logic. That in today's chips, we are using the logic gates that accepts binary bits, that is 0 or 1. It decides it decides logically between zeros and ones. The output can be either 0 or 1. But here the people are working on qubits instead of logical bits, zeros and ones. They are working on qubits. What is a qubit? It may exist in multiple states. Both 0 and 1 can come as an input. And what it will do if both zeros and come? What if it does when analogs come? Something like that. Unlike traditional chips, they manipulate quantum states through control systems like superconducting circuits. So these quantum chips, they need specific quantum gates. It will not the logical gates that we use and or gates, it will not no more, it will not be in the future world. These conditions help minimize errors, enabling the chips to perform complex calculations effectively. So these are all the components that's being proposed for this quantum chips in future. These are all being in research nowadays. Qubits, fundamental unit of quantum information. They are capable of existing in superposition and entanglement. That is, they handle both zeros and one at a time. So for that, if they want to handle zeros and ones at a time, they need a specific gates for it, right? Simple logical gates cannot go with this concept. So now they are developing new concept, the quantum gates. Then control electronics create and send signals. How it works then? How it works? Okay, we have some quantum gates and it gets some quantum qubit inputs. How it handles it? It controls and creates sends signals that manipulate qubits and execute quantum gates. They require extreme timing, precision to maintain quantum coherence and fidelity. For superconducting chips, these chips often include microwave generators and digital to analog converters. So these are all the quantum chips. They are going to rule the future embedded system. They are all still being in research. They haven't released to the market yet. Superconducting quantum chips, trapped ion quantum chips, photonic quantum chips, spin-based quantum chips, topological quantum chips. So another ongoing effort. Then what next for quantum chips? They will keep on working on to achieve better miniaturization and integration, allowing more qubits to fit on a single chip. And also mainly they are exploring 3D architectures and modular designs and new materials to scale up these qubit counts without compromising or coherence or increasing error rates. So that's it. We are coming to the final time to our session. So I am completing my session now. So any questions, please?
Participants, if you have any queries, please ask.
Hopefully, I've just so, ma'am.
Yeah,
That's it.
if you have any queries,
Ma'am,
Ma'am.
Subhashini, ma'am.
Yes, ma'am.
Thank you for valuable information, ma'am. I had one doubt. How to
Yes, ma'am.
optimize the SOC design, ma'am, for power consumption, likewise performance and area?
What is
Because
that, ma'am? Can you please come again?
because when we go for FPGA design or SOC design, we have to
Yeah,
consider the three parameters: majorly the power consumption, their
yeah.
performance, and their area. How we can optimize that design, ma'am?
Optimizing the design, it is about the develop. It is in the developer's hand, like uh, the design, the it is the different field that we can go for. It is an embedded design where we for controlling the powers, optimizing the powers. It is related to the embedded design concept. It is not related to this chip design.
Okay, ma'am. Okay.
Yeah.
Okay. Thank you, ma'am.
நீங்க கேக்குறது வந்து பவர் கண்ட்ரோல் வந்து அந்த எஃபிஜிஎஸ்க்கெல்லாம் எப்படி பண்ணலாம்னு என்ன கேக்குறீங்க?
அதாவது என்னன்னா மேம், இப்ப நம்ம வந்து FPGA வந்து ஏரியா ஜஸ்ட் ஜாஸ்தியா இருக்கு அப்படிங்கிறதுக்காக தான் வி
ம்.
மூவ் ஆன் டு த SOC. ஸோ அப்ப
அது ஒரு
SOCலுமே
கான்செப்ட். எஸ்ஓசி
ம்.
எஃபிஜி சில இடத்துல வந்து ஸ்டாண்ட் அலோனாவும் இப்போ யூஸ் பண்றாங்க மேடம். சில
ஓகே,
கான்செப்ட்க்கு
ஓகே மேம்.
தே யூஸ்
ஆ,
ஸ்டாண்ட் அலோனாவும் யூஸ் பண்றாங்க. பட் அட்வான்ஸ்டு, அதாவது ரொம்ப காஸ்ட், இதெல்லாம் வந்து எஸ்ஓசிங்கிறது ரொம்ப காஸ்ட் எக்ஸ்பென்சிவ்
காஸ்ட்.
ஆனது. ஸோ அதுக்கு அஃபோர்ட்
அது
பண்ண
நம்ம எப்படி
முடியாதவங்க
மேம்
வந்து
ஃபேப்ரிகேட் பண்ண முடியும்? இப்போ ஒன்ஸ் நம்ம சிமுலேஷன் வச்சு பண்ணிட்டோம் அப்படின்னா, எப்படி நம்ம புரோட்டோடைப்பா கன்வெர்ட் பண்ண முடியும் மேம்? இஸ் தேர் எனி ஐடியா மேம்?
அதை பத்தின
ஓகே
ஐடியாஸ்
மேம்.
இல்ல. எனக்கு வந்து ஆஃப்டர் மேனுஃபேக்சரிங் ஹவ் டு ஹேண்டில் அப்படிங்கிறது தெரியும்.
ஓகே மேம்.
நம்ம இந்த பவர் ஹேண்ட்லிங்க்கெல்லாம் வந்து இந்த டெஸ்டிங் டெக்னாலஜின்னு இருக்கு. ஜேடேக்னு சொல்லுவாங்க. ஜாயிண்ட்
ஓகே,
டெஸ்டிங், அந்த பவுண்டரி டெஸ்டிங் அதெல்லாம் பண்ணுவாங்க. அந்த இதுல
ஓகே
வந்து
மேம்.
தே சேஞ்சஸ் த டிசைன் அண்ட் சேஞ்சஸ் த சாஃப்ட்வேர் அக்கார்டிங்லி. அது வந்து இன்புட் எடுத்துக்கிறோம். அது அதுக்கு தகுந்தாப்புல கேன்
அப்ளிகேஷனுக்கு
மேனேஜ்.
தகுந்தாப்புல யூஸ்
ஆமா,
பண்ணுவோம்.
ஆமா. வி
ஓகே
கேன்
மேம். ஓகே.
either increase the output or the power levels, voltage levels increase பண்ணலாம், decrease பண்ணலாம்.
ஓகே மேம். ஓகே மேம். தேங்க் யூ மேம்.
Thanks. And convey my thanks, especially to Durga, because this is a great opportunity for me.
Thanks, Subhashini. It was nice to have you with us today. Thank you very
Oh,
much
thank you.
for joining with
Thanks,
us
Durga.
today. I
Okay,
know
thank you,
you
Durga.
are absolutely busy, but
That's okay, but
dedicating your time with us, and yeah, I know this is early morning for you, I think.
yeah, I
Uh,
have to
oh,
focus. Yeah, I am on. That's why
yeah,
I've
yeah, I know, and
just
I understand. I
hurry.
totally understand.
Yeah,
Yeah.
yeah.
Thank you very
Thank
much
you.
for your contribution today. Thank you so much.
Thanks, Durga. Thank you. Thank you all.
thank you, ma'am. Thank you for an
Thank you.
informative session in embedded systems and
Thank
emerging technologies and security in embedded systems. Thank you, ma'am.
It's my pleasure. Thank you.
Participants, will you please switch on your video to take a snap? Kindly switch on your videos. Thank you all.
Thank you, ma'am.
So kindly take some 10 minutes break and join the session after 10 minutes. Thank you all.
Thank you, ma'am.
Good evening to all. Topic of the session is engineering for real world ethical domain aware AI and IoT solutions for Industry 4.0. Now I call upon Sylvia Ma'am, Assistant Professor, EC Department, for giving introduction about the speaker, Mr. Sivapunyam sir. Thank you.
Good evening, everyone. It gives me immense pleasure to introduce our resource person for this section. Mr. Sivapunyam Dakshinamurthy is the founder and CEO of Signotech, a global consulting firm headquarters in the US, delivering digital transformation, AI transformation, data analytics, and business intelligence solutions across US, India, and Malaysia. Under his leadership, the company is focused on advancing multi-agent AI platform, industry-specific analytics solutions, and AI-powered sales and operation tools. Mr. Sivapunyam completed his Master of Computer Application at Bharatidasan University, and he started his journey as an engineer in India and built his expertise through global roles at Wipro, GE Healthcare, General Motors, and CPS Energy in the United States. He has since led data and digital transformation programs for Fortune 500 companies. Alongside his entrepreneurial work, Mr. Sivapunyam serves as an adjunct faculty at the University of Wisconsin, Milwaukee, where he teaches business intelligence, data science, and AI. A passionate educator and a mentor, he works closely with the students and faculty. With over 20 years of experience in the IT industry, he acquired a plethora of experience across various sectors, including healthcare, medical devices, and automotive manufacturing, from cloud infrastructure and cyber security to data analytics and software development. Apart from this, he also hosts Village to Valley, a platform through which he shares the journeys of people whom have transformed their life, their business, and mindset. At Signotech, they are committed to help small and medium-sized business by harnessing the power of IT. We welcome you, sir.
Thank you, Sylvia, for the nice introduction. And I appreciate the opportunity given by Professor Dr. Mangerkarsi for sharing my perspective on this topic, engineering for the real world. And then good evening, everybody. And I understand this must be a long day for all of you and still join this session to hear from me. That means lots to me. Just give me a minute. I'll share my presentation and then we'll get this conversation started. Just give me a minute. Just want can someone confirm if you're able to see the presentation?
Yes, sir, it's visible.
Yes, sir.
Right. Great. Once again, good evening all. I just wanted to have this, I want to share this conversation like a perspective. I may be wrong, but again, from the industry point of view, like, as a business owner, running an IT company, what I found today, the engineering curriculum, what's happening in the industry, like, there is an industry, the which is inventing a lot of new initiative, and then there is an academic industry generating a lot of talent pool. Everybody is working hard, but what is missing, like what is required for, our students are all learning a lot of advanced technology from engineering institute. What is missing when we are hiring the engineering student? What is that we are seeing that academic is not seeing? And this the entire conversation which I'm going to share is from that perspective, right? You're all amazing professors and lecturers, and done a lot of like, depth of studies and research, and then sharing your knowledge, training the students, pouring your heart to teach them and then make them successful. But when they complete the engineering course, when they are coming out for a job market, are they job ready? What is that we need to do? What is academic? What is that academic institute need to consider? And especially you're all faculty here. You're all better at what you do in terms of research. But what is that missing when it comes to engineering for the real world example, like from the industry point of view? That's what I want to share the next 40 minutes. Like, I know that this is 1 hour of our session, but I'm just looking at least 1 hour, sharing my thought process and then answering any questions you may have, probably 15 minutes. That's how I'm planning to organize this discussion. Let's take a look at what is the current status of academia. If you look at the curricula is focusing on covering depth of technology, like, when I see the students coming out of college, they are very good in Python, scripting, data science, like any tools and technologies that are relevant to AI, ML, and all the stuff. But they are just skilled with the technique and tools. But what is missing is domain knowledge, domain awareness, compliance, standard, applied thinking for whatever they have learned, to put that into work. The questions which we need to answer, we need to ask ourselves, right? Students may be exam ready. Are they industry ready? This is a bigger question from a business owner point of view that I ask. In the past, right, the students comes out of college, they do internship, they do good project work, and then they come for interview. But when we interview on them, when we interview them on the skill level, or if you put them through the test, pretty much they are able to pass, or they are able to qualify. But one of the key question our, like, in our company or many business owner ask, explain, like, for example, we ask one question. Now, I'm not worried about academic performance. We are not worried about academic performance or the test which they are doing. Pretty much they are able to do everything right. But one question when we ask, right, what kind of project work which you have done? This is the question that I ask. I and my team are, pretty much industry, like business owners like us, ask this question to see that are have the students applied the knowledge, applied the skills they learned from the curriculum into doing something meaningful in a meaningful project work? Are they able to explain in depth of what they have done in the project work? This is something that we look at it. Unfortunately, around, like, more than 70% of the students, they don't have the right answer for this question. Or, pretty much they do. I understand that there are a lot of pressure from the students to learn a lot of things and earn good mark to come out of the college with, like, good grades. And then from faculty community, like, professors and lecturers, they have a lot to teach in the curriculum. So they have a lot of pressure in terms of covering the syllabus and then making sure their students are getting good grades. I completely understand that where the academia is coming from. Well, what is the priority for the faculties? What is the priority for the engineering students? And I get it. But one big thing in the equation which is missing is up, application of the knowledge, applied thinking of whatever they learn. That's a huge gap. And I thought that I would share, like, some examples and how we can bridge the gap. And then I know that you all can take this information, see how you can influence the curriculum design or syllabus. Uh, See, I wear multiple hats as a company owner, and then I'm fascinated about sharing a lot of things with the students. So, in University of Wisconsin Milwaukee, I do teaching. One good thing about that university, when they gave a curriculum, they suggested that this is the framework, but I can build my own curriculum. They respected, okay, sir, from industry background, this is the title of your course, like coursework, which is business intelligence tools and technology. But you know what? You get to define your curriculum. That was really great opportunity for me. And while other professors are covering a lot of hypothesis theory and all those things, I was able to build a curriculum which is more practical, industry oriented, and all those things. With that background, I want to share some insights with you all. If you look at today, everybody think that students think that, like, oh, I learned AI, I learned data science, I learned machine learning. No, they learned the technology, but is technology equal to solution? No. The technology plus domain knowledge, compliance, ethics, application of knowledge, everything build a solution. That's where the real world is that's what the real world is looking for. And if you look at the job opportunities now, nobody have time. Earlier, right, companies had like at least 3 to 6 months of training period. They get the students in the camp in they recruit students in the camp from through the campus recruitment, and then they put them through at least minimum 3 months of internal training. But now with the AI, there are a lot of competition right now. The recruitment is going to change. Now, if you look at, right, if there is a student that, have done everything great in the academic scoring and all those things, say, for example, like, 95% of the grade but when they come to our interview, we just don't look at the grade. We just look at, has the student have done anything, have applied any of the knowledge in terms of building something real, which is closer to the real world. Today, the institutions are focusing on teaching the same thing, like, if like, the skill or tools or technology. But when it comes to application of knowledge, there is a huge gap. But when I say this is a huge gap, that is also an opportunity as well. For example, like, if in your case, I saw that your institute is autonomous. I'm assuming that autonomous institutions they have flexibility to define their own curricula. And again, today I want to share some perspective when you are teaching IoT, when you're talking about Industry 4.0, when you're teaching them whatever the technology skill, can you also consider some domain awareness along with it? Assume that you have an opportunity to build your own curriculum. And then, if you have the flexibility of building your own curriculum, what you should think, what would be the great addition to make sure that the students which are going out of your institution are job ready. That's a thought process that today I want to share with you all. Today, when I'm looking at almost like 8 out of 10 students comes and hey, so they all have done some certification in AI. They think that they know AI. Yes, ChatGPT with ChatGPT with all the AI tool, anybody can learn AI, but AI doesn't mean that learning a tool or technology. For example, if you're building some AI-based solution for a pharmaceutical industry or medical industry, awareness about compliance, that's a big addition. If your student, assume that a student coming out of college who has learned all the technical skill, plus some domain awareness, plus some compliance related to that relevant technology, I think that would be a great addition for them to be picked up for the job market. That's I just want to share that perspective with you all. From the context of this today topic, I just picked one example, like where how you can consider application of knowledge or domain awareness or additional characteristics of teaching. So I just want to share you this today. When I was talking to Professor Mangekar, she was telling that, sir, whatever the topic which you're talking, can you make sure that that is industry 4.0 related? Can you make sure that that is IoT related? Can you make sure that that is AI related? So I thought that I'll bring this kind of multi-layer. Uh, if you look at this picture, right? Typically, any industry 4.4 solution has multiple layer to it for a manufacturing industry. This one will give you a comprehensive view of, assume that you are building a curriculum, you are training your students, they're like for aligned to some technology or some skill, how you can structure your thought process. If you pay attention to this diagram, then you will be able to understand more. For example, in industry 4.0 solution, for a typical manufacturing, if you think about everything that is happening in a manufacturing industry, you see the bottom of the layer, it's all like a physical layer in a manufacturing, like what are the sensor, like what are the machines involved in it in the manufacturing. And that's where the foundation aspect of manufacturing solutions. And then on top of it, if you look at process controller, PLC controllers, and PLC programming, control system, robotics, process automation, real-time machine coordination. That is the second level of the layer. And then third level of layer is like MES, the manufacturing execution system. And in a manufacturing execution system, you go in depth about production scheduling, quality management, and then the students will learn a lot about MES tools. And then the next layer is ERP, enterprise resource planning. That's where the applications like SAP, Odoo, financial solution, supply chain management, business process management, and then on top of it, artificial intelligence, IoT, data analytics. And then if you look at top most layer, like, compliance, like compliance relevant to the manufacturing industry. If you look at, if you're developing some software solution for manufacturing industry, specifically in US, the expectation is that learning about the various standards like data governance policies, and then GDPR, like data protection policies. In the healthcare industry, it's called HIPAA, Healthcare Information Privacy Act, and then NIST is another governance control. But if you look, this is something that I brought it to you guys to share with you. Let's talk about. I'm not sure that what are the coverage of your subject matter in this audience right now. But let's take an example. If you are if you're tra- if you are if you have a curriculum, if you have a syllabus which is talking about industry 4.0, you may, like there are certain if you're training them on AI, you will focus on what kind of data that are generated by ERP systems, what kind of data that are generated by manufacturing execution system, what kind of data which are generated by PLC system controllers that need to be used by AI. So today, if you're only teaching Python scripting and some models like AI models, some ML models, they will learn with some sample data. They will use the tools like, NumPy, Python, or, Panda. There are like tools. You just give some example, they read it, they practice it, and then they, whatever the exam which you are conducting, they will score more than 80%, come out of the college. But is it good enough? How AI is used? If the students, if the, have we taught AI from the context of industry 4.4, 4.0? Are they able to think AI in terms of the manufacturing domain? This is the question that I want all of us to think. In this case, right, 360 degree of industry 4.0 solution that includes awareness about every layer. Not that everybody need to know everything about every layer, but at least awareness, like, for example, like someone is learning to learning the embedded system, like system programming. They learn everything at the bottom layer, like what device is used in the manufacturing, what kind of programming control system need to be developed, what is input to the device, what is process the device is doing, what process the device is doing, what is the output of the device, how that device is interacting with the other devices. That is the depth in that layer, in addition to doing simple system programming. When I'm looking at college curriculum, they focus on embedded system, like, simple, like, C program, programmable control and all. But again, have they applied that knowledge for a particular manufacturing industry, for a particular device? This is something that we need to ask ourselves and see that if there is a gap in the curriculum, how do we address the gap? The same way, the PLC, like, when we are learning PLC programming, probably we will do within our college setup, whatever the lab setup we have, simple PLC programming we do. But are we able to do something that real-time application? Are the students are able to go to the factory and trying to see that how the PLC controllers are used exactly in an injection molding, in the injection molding operation, or in a shop floor automation, how the PLC is playing a major role? That's something that we need to think through. If you guys have, if your curriculum is including this, that's great. But if not, this is time to think about it. And then MES layer. So many times, right, like, the comprehensive overview of like what's happening in manufacturing execution system, and then top of it, ERP. See, many time, software engineer will go learn SAP or Voodoo or some financial system, and then when they go to work, if they don't have awareness about all other layers of this particular industry 4.0 solution, they may not be able to ask relevant question to the subject matter expertise. So, and then if you look at, right, every layer, and then when they're writing a software, if they don't take care of all the security control defined by a NIST or ISO or HIPAA or GDPR, they may not be able to do something relevant. My point is like the whole concept of educating our students with the domain awareness, instead of just teaching them the, just like, the software tools and all those things. How much of domain awareness that we are creating? That's something I just want to share from this particular conversation. So I'm not sure, like, I just wanted to make sure that this little bit of interaction. How many of you, like, can you guys, I'm just going to can you guys say in the chat window, how many of you are aware of this industry 4.4 layers which I shared? If you know, just type 0. Sorry, type 1. If you don't know, type 0. I just want to understand that. 1. Okay. All right. How many ones? Okay. Right now we have 125 participation. I want to hear from many of you. How many of you are familiar with this industry 4.0 layer which I talked about? Okay, 0, 1. Let me hear from more people, guys. Like, I just want to make sure that everybody
Sir, voice is breaking.
how about, can you guys hear me now?
Yes.
Yeah. Hey, so the more than 127 participant, I just want to hear from you that if I hear more one, I will be able to structure my conversation accordingly. If I see more zero, I'll be able to go a little bit more detail. Fortunately, I see a lot of one here, so looks like that you guys are familiar with it. So I'll go a little bit deeper into it. Like, the when you are talking about engineering for real world, uh, awareness about all the layer that I talked about. And then number one is awareness about all the layer. Number two, re-looking at, are we able to look at your syllabus to see that what is missing? How do, if your syllabus is not covering this, how do we bring this particular content? How do you, like, for example, like today, if people are expecting a differentiation, right? And assume that your college is focusing on more than, like, more than just a technical skill. Your college is focusing on adding some syllabus about NIST control. The NIST is one of the control, governance control used for all the manufacturing that talk about, your operation, information security. There's a lot of things that. So are we able to add some curriculum that will create awareness about NIST for manufacturing? That is that. And then, when we are teaching about process control, are we able to talk about how this layer, like, the PLC program is integrating with some software applications that are available in MES layer, how the MES layer is communicating with the ERP layer, how all the data which is created. If you look at every layer right now in this industry 4.0 solution, they create tremendous amount of data. In the past, the device layer will only keep the data at the device level layer. It's the ability to pull the data and then use it across the layer was not the case. But now with the modern technology and data capabilities, you can pretty much create a data lake, and then get the data from every layer. When it comes to device layer, sensors are creating some data, like, analog data and digital data that you can parse and add some context and then put it into data lake. And then PLC controllers create some data, sensors can create the data, MES system create the data, ERP system create the data. You can put all the data coming from all the layers. You can apply artificial intelligence capability at all the layer. That is the kind of technology advancements that's happening now. If you look at, right, every layer used to be isolated, but now when you number one, creating awareness about the layer and creating awareness about data generated from each and every layer, how to use that data for artificial intelligence. That's the kind of thought process that I want us to think through when we are building curriculum. And that way, it will also be very interesting rather than focusing on the tools and technology. And then you can create more research, you can create more innovation at the college lab level. So that's the kind of a thought process that I want to initiate from this conversation. I hope it is helpful for you to understand layer. I'm going to go into the little bit more detail in each and every layer. If you look at, right, 1 minute, which layer we are talking about? Device layer. If you look at device layer, so look at your curriculum. How much, like, what are the things which we are teaching? typically skills requires are embedded system, electronics, signal processing, and maintenance. That is skills required. But how the skills are application of those skills, right? In terms of smart sensor, connected device, machinery, conditions, monitoring. Are we able to go deep into this? Is our current systems going to that depth? That's something that I want all of you guys to think through, right? And skill everybody is covering, all the institutes are covering. What differentiation that your institution can make, what differentiation your institution can do to create job ready talents coming out of your college. And are we right now, are we like, the impact of this thing, right? For example, we use Heroku Cloud. If a sensor, we capture the data from all the sensor, and then the AI model is useless if they don't know how the data is born, where the data is generated. See, if I look at, right, there is like, the current syllabus have pockets. One pocket will be teaching embedded programming, and then signal processing and maintenance. But what, like, how to apply that, what data is generated, how to interpret the data, what kind of analytics that can be done on that data, what kind of AI use cases, that something is missing. And again, it's not easy. It is not easy just to build the curriculum or doing that. But if there is a synergy between educational institution and then the industry, you can build all the layers, all the aspect of the curriculum. Right now, I'm sure that the skill is covered, but looking at application and impact is very important. Like that, I'm going to go through each and every layer that we can analyze that. So if you are a professor talking about teaching that embedded system, it's it's very important to look at that, what layer that embedded system is in the industry 4.0, and application of that embedded system, and what kind of data awareness, what to do with the data. Those are the things that you need to start thinking about integrating into this curriculum. I want a quick check. Are you all following? Is this making sense? Is it interesting or boring? It's very important, because since I'm not seeing you all. If it is interesting, one. If it is boring, zero. I'm okay with any feedback. Is it making sense? I want to see a couple of one or zero. Looks like it's a long day. Okay. Great. Thank you for sharing that feedback. That makes, it's very difficult in Zoom to check, what's going on in the audience mind. Okay, let's look at the control layer now. So if you look at control layer, right, this is where the process controllers are, process control, and network, communication between one sensor to another sensor, or assume that, if you are talking about a huge injection molding, in an injection in a manufacturing plant, an injection molding, depending on whatever the tool or die cast they are doing, there is a sequence of recipe, and then the PLC program need to make sure that the mold is properly inserted, the recipes are properly loaded. There are so many processes there in an injection in a manufacturing plant. And then when we are focusing on just a skill, probably we may teach basic PLC programming skills, but how it is applied in the industry setup, and the program, how that each and every PLC programming unit is interacting with the others in an end-to-end manufacturing scenario, and then the applications of robotics control, process automation, machine coordination pretty much need to be added to the syllabus, so that you are teaching something which is closer to the real world. Again, it is very difficult only sitting in academia to think this way. Again, there is an industry collaboration. If you are working with an industry to see that what is that you are teaching, and then at least taking couple of industry example to see that how the PLC programming is implemented in the factory setup, how the programming interfaces are interacting with others. This is the kind of this is the kind of thought process that I want you all think through from Industry 4.0 controller layer. We talked about device layer, which is physical, and then the next layer is control PLC controller. So we talked about skills, application, and impacts, right? And then let's look at the next layer. MES layer, right? Pretty much, if you look at, right, this layer is basically talking about your manufacturing execution. Assume that you have a CNC machine. It's programmed to do some machining operation. These MES tools are just performing. It has input output operation. You do a CNC programming at the MES layer, but we many time, right, the CNC programming focus on programming the machine and defining the input, defining the output. But the machine operations generate a lot of data. How the data is used for analyzing and productivity of that operation. Pretty much those are the additional input which you will not get from your curriculum side of it, but you need to go you, you need to partner with the industry to look at it, like how MES tools are using in this layer. And then if you for example, right, assume that the AI defect detection model, which is developed in isolation with a 95% accuracy, but it was not integrated with MES, because many times when we talk about AI model, we create synthetic data, trying to see that, like even create some sample data which will have a defect, and then we only focus on the outcome of the AI model. And then you will fine tune, just say that by looking at the synthetic data, you say, oh, 95% accuracy. But have we integrated that with MES? What kind of integration is happening in the real industry scenario? That is very important. Just AI alone is not going to help. This is where, again, we need to go deep into the MES layer to understand that. Especially in today's theme, that Industry 4.0, every layer need to look at all the aspect of it instead of looking at just skill or programming and technology aspect of it. And then, I'm just going into the ERP layer. This is something I found that even from my own experience, right, until I completed my Master of Computer Application, until I go to the job, I did not have any awareness about ERP. But I'm talking about like 25 years ago. But now, if you are, if you're talking about Industry 4.0, if you're only focusing on all other layer like sensor and IoT, if you're not giving enough understanding about the enterprise resource planning system, they'll come out of it and then they'll just go into their domain without knowing this complete picture of how ERP systems are used in Industry 4.4. But think about the other alternative, that we define our curriculum in such a way that we talk about all the layer when this candidate is going for an interview, not only talking about the technical skill, talks about all other domain awareness, like, for manufacturing domain awareness, and then that candidate will stand out. And then even as a faculty teaching, taking the same syllabus, teaching again and again to cover the syllabus versus applying this industry reality into the curriculum, that will be very interesting. And then if you look at now, I'm sure that most of the academic organization, they are not looking at their professors just delivering the syllabus, grading the students' outcome. They are looking at the professor to see how much they are driving innovation. What kind of research they are doing, what kind of grant they are writing. So for that, if you're only doing academic point of view, you will be right publishing the paper, but industry is not looking at. Now, I- I'm assuming that even in India is happening, but if you look at UW Milwaukee, they have a IoT connected device center of excellence where Microsoft pouring a lot of money, and then Intel is pouring a lot of money, and then they are giving budget to university. Instead of hiring the student as an employee, they are giving a mini project to the university, and then they are giving education, and then they are taking the project work done by the students. So now, instead of now the students and lecturers are working as a, though they are not part of though they are not part of the industry, but they are becoming an ancillary part of the industry within the university campus. They learn everything about it. They build something that can be used by the industry. This is the trend which is happening in US, and I'm assuming that even in India, a lot of incubation centers are being formed, and universities are creating incubation center, trying to take project work from the industry into the campus. That's the trend which I see. But if we need to be prepared for that, now students are not just students. They are indirectly working for the technology industry. Faculties are not just delivering the lecture, they are guide, they are architect building solution for engineering students. That's the trend is happening. And then that way you also feel like you are contributing to the industry, not just delivering the lecture or covering the syllabus, making the students scoring a high grade. That's the trend which is happening. Then you will not miss out by not being in the industry. You will enjoy the benefit of teaching as well as contributing to the industry. That's the thought process that I want to share. This is the ERP layer. Now, the now the entire world is talking about this layer. Like, guess who is not, like, let me go back. AI, IoT, machine learning, analytics, predict, predictive analytics, preventive analytics, everything to do with the data is happening in this layer. If you look at, right, if you are only focusing on skills like AI, ML, data science and all, like we will teach like that, whatever the libraries available. If you look at, we are not teaching AI, we are only teaching them to choose what model they, you know, I'm not, I've seen AI curriculum, nowhere I have seen AI curriculum going to the deep depth of, building a mathematical model, because those models are already built. Mostly in the name of AI, what we are doing is basically we are picking the algorithm, we are using a tool, we are we are just dragging and dropping the widgets of the tool and choosing the algorithm, passing the data through the algorithm, and trying to do that machine learning and supervised machine learning, unsupervised machine learning, all these things. Those are all like widgets. Somebody developed it. Nobody, you know, but now what focus we need to do, even to decide what algorithm to choose, you need to know in depth about application of the AI, and then you need to teach the domain expertise on the manufacturing industry. For example, like we developed a solution for a mattress manufacturer. In US, there is a company called Future Foam. It's a mattress, that the mattress manufacturing company, where they collect the data from the sensor, the moisture, every 5 minutes interval they will collect the temperature, and in the temperature should be in a particular range for the mattress to be perfect, otherwise it will not it will be defective. So now you need to understand the mattress industry. You need to understand the role of temperature, the criticality of the temperature, why we need to measure the temperature. Then you need to collect the data, detect the anomaly, and then pass the feedback loop. For example, if the temperature is very below from the threshold, you need to pass the data to the feedback loop so that the system is adjusting the temperature. This kind of context will not be available right now at the academia level, because we only talk about the theory and then programming aspect of it, data aspect of it. But now if you add that, right now the expectation from the industry is such that if there is any academic industry, any academic organization focusing, They are going to that academic organization, building partnership with the academic organization, hire students in the third year, fourth year, hire the faculty as a mentor. They take the students and faculty to their factory and teaching what the factory is expecting. And then, they are trying to get that from the university campus. Once they build something, they are able to acquire this talent to their organization, or they are able to start something as an incubator. This is what happening in the industry right now. So AI without awareness about what model to use, how the AI is applied for the business, applied for decision making, applied in the manufacturing setup. Without that awareness, everybody know AI. With ChatGPT, everybody can prepare for interview. But this is what the differentiation that industry is expecting, whether it is this layer like IoT, AI, and data layer. Students are, the students need to think through that, the data, how the data is used, like what is the impact of the data, what is the impact of the AI solution which they are developing in they need to start thinking through. Our curriculum should start including these things also um, uh, at this layer. The next layer is that compliance and ethic layer. This is playing huge role in the industry now. Like, if you look at, right, people are talking about ethical AI. What, like, AI, how to make sure that, the data which is whatever the large language model which we are developing, if you are utilizing that for a particular industry 4.0 solution, how to make sure that data relevant to that industry is pumped into the LLM without breaching the security, and how to make sure that LLM models are trained in such a way that the context of the model, context of the particular application of the solution is trained in a secure manner. How to prevent that AI from hallucinating. There's huge emphasis is happening at this layer. Like, are we, whatever the industry, whatever the skill which you are learning, application of the skill from the context of the industry regulation, compliance, security requirement, and boundary context. This is something like, is being looked at right now. It's a huge area that everybody is focusing on. There could be a one paper compliance. There could be a paper like an application of AI with the awareness of the compliance. If you look at every industry has a compliance, like, financial organizations have a compliance called SOX, and then healthcare organizations have HIPAA, FDA, CFR Part 11, manufacturing organizations have NIST. So this is the layer. If an institution is focusing on training people in this layer, and then the students coming with this kind of knowledge, they straight away go as a consultant, not like, cream of the cream, not like just a programmer. There are a lot. If you look at the pyramid or the layers which we saw in the industry 4.0, every layer have unique opportunity in the industry, right? Um, Look at it. So now look at, especially if your students are working on AI and IoT, or and the learning, or they are trying to get into the job market with this particular space. This Anybody who has understanding on this, right? You know, how to use the right algorithm, how to prevent AI bias, how to use the right data, where to use synthetic data, how to like, what kind of data which is relevant. And then when we are developing a software on top of IoT devices, are there any security related issues over there? Because today, if you look at our, like, people developing sensor focusing on input output process, but when we adding additional security layer, it will be added advantage of, learning that IoT development. So this is another area where, um, I would require, like, we need to relook at our syllabus, our curriculum in such a way that, we are adding this aspect of it. That will become very unique. Your students will become, your organization will be very different from any other organization. Because if you look at an academic industry, where to make the difference? Are we teaching the same thing, or are we looking at the curriculum which has domain awareness, application of knowledge, industry regulation, and pretty much, is it are we covering, is our syllabus is well rounded, compare adding all the aspect of it? That's the question that I want all of us to think through, and then see what difference we can make. Uh, Again, if you look at, if I were to provide some kind of recommendation on how, what kind of curriculum would address all this concern. You look at right now that your distribution, right? Everybody is focusing maybe like 80% technology and fundamental, but ignoring domain awareness, compliance and standards, and ethics and ethical and responsibility. But if you want to build a well-rounded curriculum, which will create job-ready people, which will be very close to the reality. When I say that real world engineering capability, I would say that we need to look at this kind of a distribution. Number one, our own learning as a faculty. Number two, adding as part of the curriculum. If you are not able to influence the curriculum, at least making sure that the students are applying all aspects in their internship work, applying all these aspects in their project work. That will itself. I'm not. I'm not aware about the current curriculum. The what do you call it? What kind of freedom you guys have? And I studied in a autonomous college, and unfortunately, I'm talking about even 1998, the institute where I studied, they had a flexibility to define the curriculum. And I'm one of the product from that institute. But here, if you are affiliated to the university, if the university is pushing the curriculum that you need to control, you don't have any control, I completely understand. But if you have flexibility, thinking the curriculum in terms of this. If you don't have the flexibility, at least pay attention when you are giving a project work. Just pay attention to your student. Make sure that your students are applying all these aspects of a solution in a project work. That itself a big deal. And then you are making a huge difference by making them doing that. With that, I just want to conclude my thought process, whatever I prepared to share with you. But I want to interact with you. I want to address some questions. So I'm going to stop my slides. I'm going to say that I love guiding, inspiring students. And that's why, even though I'm in the industry, I chose to do adjunct faculty role in a university like that. I hope whatever I shared was useful. Now I want to hear from you. If there is any question I want to address, just give me a minute. I'm going to stop sharing.
Participants, if you have any queries, please ask. Participants,
Anybody shy, you can text your question in the chat window. I will answer.
Sir, I have doubts, sir. When
Mhm.
you are preparing the students for the real world challenges, how can we integrate the ethical thinking into uh, technical training?
Great question, right? So when they choose a problem, assume that if they're developing some as part of their project work, they are developing something. Okay. Um, what they pretty much what they do is that they look at the problem definition, they look at the solution for the problem. But beyond that, we need to suggest them, okay, that problem is part of which industry that problem is relevant to. For that particular industry, what is the compliance requirement? What kind of do's and don'ts for that particular industry? Are we able to add that part of our solution? If you look at, right, I just remember when I was doing my physics, and at that time we had a we were building my project work was for like interruption counter. It is basically we had a sensor, like, if somebody go through the sensor, it will just count the number of people. I mean, I'm looking at that was so silly. I'm talking about 20 years. We thought that, okay, I'm doing a big project because we need to use some digital, what do you call it, digital flip-flops and other things. We build it. But now if I'm looking at with the recent technology, we need to think about what is the application of that interruption counter, what industry that is going to be used. In that industry, if the counter is not working properly, if the particular project is not delivering, if it is not working positively, what could go wrong? Are we able to put the negative testing scenario? Are we able to put all the positive testing scenario? Pretty much we need to make them think through that. Like, see, right now we are all focusing on the problem which you're solving, but again, that problem, that particular project, what industry relevant? For that industry relevant, what can go wrong? Did we include that as part of our solution? This is where this ethical aspect of it, compliance aspect of it will come.
Thank you, sir. Thank you.
Any other questions, guys, from anybody? Okay, if not, I know that this is a 1.5 hour, but again, I kept a lot of things for discussion point of view. If there is no much questions or discussion, probably we can conclude this conversation now.
Participants, please ask any queries.
I am very happy to see still 126 participants are there in this, and and I'm glad to see, because on a day like this, around 8:25, somebody listening to something, that's commendable. Can you give some advice to students who are willing to take embedded as a career? Amazing. So now AI is in the past. If you look at right now, what's happening in the embedded industry, adding IoT and then artificial intelligence and edge computing, all these things have a huge demand. If you look at, like, in the traditional the curriculum, they will talk about writing some program at the chip level, but now adding how to connect that device, like, you not only you need to write a program and embedded using embedded, but you need to make sure that that is connectable through mesh network or mesh wireless network, mesh Bluetooth network, whatever it is, and then it transmit data, and then it applies some artificial intelligence at the edge level. A lot of interesting things are happening. And then don't just think that embedded is nothing. You just, when you're choosing embedded, think about, you are choosing AI, you're talking about Internet of Things, and then that device is communicating with the other device. It's a very interesting thing. Huge demand is there. But again, not just for doing embedded, you need to think application of embedded, with AI and IoT, then there is a huge demand in the market. See, now, right now, if you look at, right, in the AI world, there are a lot of computing power is required. Now people are talking about, assume that you're doing some embedded device, or you are writing some program to monitor camera. How do we do edge computing? Even if there is no, if there is no internet, what can be done at the edge level using Bluetooth, using radio wave? These are the things are still being looked at in the industry. If any of you guys, any of your students are doing that kind of project work, that will be a, that will, there will be a lot of innovations happening around that edge computing. In a device, edge computing is very important nowadays. All right, if there is no further question, I think I can conclude this session. Thank you all for this opportunity. Wish you all have a wonderful curriculum designing moving forward.
Okay, thank you, sir. Thank your presentation has been invaluable in bridging the gap between what we learn in our institutions and the practical demands of the industrial world, offering us a clear roadmap for the future. We are especially grateful for how this session has been helped to connect the world of academia with the real world challenges of Industry 4.0. Okay, thank you. Thank you, sir.
Welcome.
Participants, please switch on the camera for take a shot. Feedback form now available in chat box. So participants only fill the form, then you can leave. Okay, thank you.